and thanks for tuning in. Today's video is a little bit different to what I originally had planned. Originally I was going to make a video describing how I designed and then made the Beast Car's body shell, but actually I realised that I wanted to explain a bit of a science behind why I think the body design is really important for RC speedrunning. So in this video I'm going to try and unlock some of the mysteries of aerodynamics and how it affects our RC speed cars. So I hope you find it interesting and maybe even a bit useful. Let's get stuck in.
There's plenty of challenges to RC speedrunning, and I'm going to explain one of them now with a few little diagrams. So firstly, when you're doing a speedrun, you put your car down as far away as you can from where you're positioned, which might be up to about 500 meters perhaps, depending on how good the visibility is. I mean, we're trying as hard as we can usually to get that distance as high as possible by standing on a step ladder or something to get higher up and be able to see a bit further, painting the car in bright colours. Some people do that, and maybe even putting lights on the car. The next thing is that the speed trap that we've got, that might be only about 100 meters from where we're standing. It depends how you're measuring the speed. If you're measuring it with an onboard device, then that obviously doesn't apply. But at the roster events, this is a typical setup. So the takeaway from this really is that we've got a limited distance with which to work with and accelerate our car up to the top speed that it gets to before it goes through the speed trap. So just to demonstrate that again and describe what we want to achieve, a simple graph. So speeds on the vertical there, time on the horizontal. So over the time and distance available, covering the 600 meters, we want to get up to our very fast speed, whatever that is, beating our personal record, reaching our goals for that particular car. And to achieve that, we're going to have to accelerate the car. So it's going to have to go from 0 or near 0 up to that very fast speed in the time available. That means it must accelerate. So on the next few slides, I'm going to explore how we actually achieve that. And it comes back to a fundamental equation. It's actually Newton's second law of motion, which is force equals mass times acceleration. I prefer the rearranged version of this, which is also more relevant, I think, for us RC speedrunners, and that is that acceleration equals force divided by mass. From looking at this, you can see that with the mass of the car being fixed, that's like a fixed quantity, in order to accelerate the car, we're going to have to provide some force. So next I'm going to look at where that comes from. What I'm going to describe here is only really relevant for wheel-driven cars. Doesn't apply to rocket, jet or fan type cars. But the way a wheel-driven car works is that the wheel gets turned with a torque by the power system, whatever that is on your vehicle. That provides a tractive force at the contact patch with the ground. The road doesn't move, so it actually pushes back on the tyre, which is where this friction with the surface comes in, and that has the effect of accelerating our vehicle forwards. So the question in terms of, how much speed can we get on our speed run, it comes back to how much of this force we can get, this friction with the surface. We obviously want to get as much of that as possible to get as much acceleration as possible to then get the highest top speed. And surprisingly enough, another simple equation is going to tell us how. And that is just that friction force is equal to the weight acting on the tyre multiplied by the friction coefficient. And in the case of a rubber tyre to asphalt or tarmac, that coefficient of friction is around 1, which is actually quite high for friction coefficients. In not many situations you get a friction coefficient that high. In It may be different for a foam tyre on tarmac, but in the absence of any sort of measured correlated data, that this is the best estimate that I've got at this time. We're going to take what we've just learnt about friction now and put it into our equation from earlier. So the equation was acceleration equals force divided by mass. That force is going to come from the friction. So that is going to be taken up by these terms here. So U is the coefficient of friction, and mass times gravity, that is the weight of the vehicle. That's then divided by mass as per before, and the two mass terms actually cancel out. So mass divided by mass equals 1. So the equation can be simplified to just coefficient of friction times gravity. So that means if your coefficient of friction is 1, the most acceleration you can get is 1 times gravity. So that means we should be able to get the same acceleration horizontally with our speed car as you'd get if you dropped it off a tall building and accelerated downwards due to gravity. But what does that mean in a practical sense? Well, let me just give a bit of a demonstration here. So if our target speed was 200 miles an hour, and we accelerate at that 1g maximum acceleration that's provided by our coefficient of friction of 1, we can get to that speed in only 9.1 seconds, which is pretty amazing. And it would only travel 407 meters, which is well within our 600 meter target that we started with. So wouldn't it be amazing if we could achieve that? You know, it would potentially make our 200 mile an hour speed target quite well achievable. However, as you can probably see, probably guess where this is going, there is a but. What I just described on the previous slide would only be possible in a vacuum where there's no air, because there's this thing called air resistance. And a typical experiment done to demonstrate air resistance is to drop a feather in air and in a vacuum and compare the two. The feather falls much faster in a vacuum, where there's no air resistance. And that's actually what we've considered so far. So that isn't a real situation. There is, basically there's this force that acts against what the force that's trying to accelerate our car. It acts against that, and that's called air resistance. There is other resistance forces, but air resistance is by far the most significant, especially as you try and go faster with your vehicle. And we'll see why that is on the next slide. This is the last equation, I promise. And it explains that faster equals draggier, the drag equation. So what this says is that our drag force that we're looking for, so we can understand how much effect that has on the vehicle, that equals a half times air density, which is what's meant by this funny looking term there called rho, multiplied by velocity squared. So the velocity here is the relative velocity of the car to the air, and it's squared, times by coefficient of drag times area. So I'm going to pick out a couple of important aspects of this, and one of them is that the velocity squared is particularly important, and that the reason for that is because of that square term. What it means is that if we times our speed by 2, the drag force is going to go up by 4. If we times our speed by 3, the drag force is going to go up by 9. And we don't have much control over that velocity term. So, this is something that we can't get away from with our RC speed running. I mean, you could argue if you ran with a massive tailwind, it would reduce the relative velocity, so that and reduce your drag force because that V term would go down. But that isn't really something we can control. I mean, it's similar with the air density actually. On a cold day, the air is more dense, so that would increase the drag force. And again, that's not something we can really control. That's something that's maybe useful to be aware of, but we can't really actively set out and try and create a situation with low air density. The other interesting ones are this drag coefficient and frontal area. Those are affected directly by the shape of our car, which is something that we can actually affect, which is why the body of the car is really important. So we're going to explore that in some more detail next. So the way we're going to explore that, we're just going to look at some typical drag coefficients and areas and the product of those, which is the CDA, and because that's what directly goes into the equation. We're going to explore that for some typical vehicles and a shape. So firstly, the cube, just a square shape being pushed through the air. That's got a very high drag coefficient of just around 1. I haven't included the area terms because that's just relative to whatever size cube you decide to use. The next one is a car that's quite similarly shaped to a cube, the Mercedes G-Class. This is one of the worst performing cars in terms of aerodynamics. But it's interesting that even this worst performing car is still significantly better than just a plain cube. It's a drag coefficient of around 0.54. It's about half of what a cube is. But it's got a very big frontal area. So that this area here, it means the projected frontal area. So if you look front on the vehicle and traced its outline on the wall behind it and then measure the area of it, that is what this area term refers to. So the overall CDA 1.6, so we'll see what that means as we look at the other ones. The next one is the original Volkswagen Beetle. It's also got quite a poor coefficient of drag of nearly 0.5, but its area is much less than that of the G-Class. So its overall CDA is nearly half of what the G-Class is. So yeah, we're starting to see that it's both of these terms together, they're important. The next one I've put in is the Toyota Prius. So this comes in when car manufacturers started to think about the aerodynamics of a car a bit more, because they're obviously thinking about fuel economy on this car. It's a hybrid, isn't it? If we can reduce the drag force, that also helps the fuel economy. So it's got quite a good coefficient of drag of 0.29, a high-ish frontal area of 1.99, but overall, because of that reduction in coefficient of drag, it's got a very low CDA. So I've got a few more examples to follow up with that. They're generally on an improving trend, but the next one is the Tesla Model S. This is one of the most aerodynamic passenger cars that exists. They put a lot of attention into the drag coefficient of this car. Because it's a pure EV, it can help maximize the range of the car. So they achieved nearly 0.21, so a very low value. But a slight problem they've got is that the area of it is quite high at 2.7 meters. So projected frontal area is high. That gives a CDA of nearly as high as the Toyota Prius from before. So again, it shows that it isn't just either one of these terms that's important, it's actually the combination of them. Typically, car manufacturers only quote the drag coefficient. They say, oh, they've achieved a great drag coefficient of 0.21, but it's on a vehicle that's like the front of a house coming towards you. And so the overall result isn't that great. But anyway, yeah, they've definitely tried with that car. This next one is a prototype Volkswagen that achieved an even better coefficient of drag, and also a very small frontal area, so gives a very good CDA value of about half of what the Tesla is there. The next one is a dedicated land speed record targeting car called the JCB Diesel Max. That took the land speed record for diesel vehicles. A few years ago, it set a new record of 350 miles an hour, and it was a car that I was actually able to find a scientific paper on that described how they developed the aerodynamics of it, and so that was quite a useful bit of information for me. And they quoted the values they achieved, which are seriously impressive. So a drag coefficient of only 0.146, an area of 0.9. So that means that looking at the front of that, you can only see 0.9 meters squared, which seems tiny. And again, our CDA value is pretty much halved from the previous vehicle we looked at. Finally, for a bit of fun, I thought I'd put in my values for the Stevenge cone, my first RC speed car, which it gets its name from the fact that it's a car crossed with a drone. Its coefficient of drag value wasn't great at 0.28, but the frontal area value of only 0.01, which is equivalent to only 10 centimeters by 10 centimeters, that has given it a very low CDA value of 0.03 or 003. So again, now I'm going to show what these values actually mean by giving a few examples. So what have I got here? I've got a car accelerating in a vacuum, which is the same as the example I showed before. So it goes from 0 to 200 miles an hour in about 9 seconds and 407 meters. But we know that that isn't possible. My second example is what I've called car 1. So it's a 10 kilogram car with a drag coefficient of 0.2, which is quite a good value, and quite a low frontal area of 0.04. So that would accelerate to 200 miles an hour in just under 11 seconds and 524 meters. So you can see that inclusion of the aerodynamic drag, even though its parameters are very good, it still causes a significant difference in the acceleration of the vehicle and whether it can reach that top speed within our targeted distance or not. I mean, you can see how the effect of the aerodynamic drag increases as the speed goes up. Like these two curves, like from the one in the vacuum and the one with the drag, diverge more as you go faster. So next we're on to car 2. So it's the same massive car with a 0.3 coefficient of drag, which isn't that dissimilar to some of the other vehicles we looked at a minute ago. But the frontal area is also slightly increased. So 0.06, that's equivalent to around the size of a sheet of A4 paper. And so the CDA value, that's just over doubled from car 1 to car 2. The effect on the time and distance to get to 200 miles an hour, though, is significant. I mean, you can see it takes 18 seconds and 1,083 meters, so more than double of what car 1 could achieve it in. Finally, we've got car 3, which has got the same area as car 2, but a slightly worse coefficient of drag of 0.4. This one's quite interesting because it doesn't actually ever reach 200 miles an hour. It peaks at 180 miles an hour. And the reason for that is that at 180 miles an hour, the drag force is equaling the force that can be provided by the friction from the tyres. So the powertrain could be trying to drive the car faster, but there just isn't the friction there to support that and overcome the massive drag forces that it's experiencing because it's got that high coefficient of drag times area value. So that, to me, shows just how important the coefficient of drag and the frontal area of the vehicle are. Also in here, I'm going to introduce this power consumption value just because it'll come in useful on the next slide. So where I get this from is multiplying the maximum friction force that the tyres can provide by the speed of the vehicle. So force times speed equals power. That's why it's basically the same for all these first three vehicles. I mean, this assumes that the car is accelerating at the peak of, or it's using the peak friction the whole time, and it assumes the powertrain can do that. And it explains why car 3 is a little bit lower because it doesn't achieve as high a top speed, so it can't lay down that extra power that's going to give it that higher top speed. So you might find yourself asking, well, you know, if you've got this higher drag value, is there anything you could do to get to the 200 miles an hour in a shorter distance? And there is a couple of things you can try. So that's what I'm going to look at on this slide. So I'm going to look at what the effective mass is and the aerodynamic downforce. So to introduce this, I've got the first three curves from the previous slide. So our vacuum ideal state, which is a straight line, our car 1, which has a low CDA value, and I've also got car 2, which has got the slightly worse CDA value. Firstly, we're going to take car 2 and we're going to add 5 kilograms of mass to it. It'll be interesting to see what that does. What happens is the extra mass increases the amount of friction with the ground, and then the friction force becomes greater in proportion with the drag force, which means as long as the powertrain can deliver enough torque and power, then the acceleration can be greater, and we're able to reach 200 miles an hour in only 629 meters, which is a massive improvement over where we were before. But that does come at a cost. You know, that requires the powertrain to deliver more than double the peak power, so 21.9 kilowatt instead of 9.7. Because of that, you know, we've got the extra friction. We're saying that we've got the extra friction with the ground from the extra weight, and we're going to use that by applying more torque through the wheels. The second option I'm going to explore is aerodynamic downforce. So I've added in this aerodynamic downforce ratio of 0.3 here. So that means that compared to the drag force that's acting on the car, we've got 0.3 times that drag force pushing the car down onto the road. What that means is things like Formula One cars have wings on them. Those are there for that purpose, so they'll be producing a downward force which pushes the car down, adds weight onto the tyres, increases the friction. And it's quite a benefit of it is that it's proportional to aerodynamic drag. So that extra downward force is there when you need it. So when you're getting faster and you're experiencing higher aerodynamic drag, you get this aerodynamic downforce that pushes your tyres into the ground and allows you to drive harder against the ground to counteract the drag force. Again, assuming that your powertrain can provide that extra force. However, it's not all plain sailing. It's hard to add the downforce without also adding to your drag coefficient. It's common knowledge really that Formula One cars aren't particularly good in terms of drag coefficient, but they can achieve better lap times by having a poor coefficient of drag but having the downforce. So anyway, with the downforce, we're achieving it in a distance of 651 meters. So, you know, we've made a big improvement with either mass or downforce towards our goal of matching the car one's values. I mean, ultimately, what I feel that this shows is that it's the drag coefficient, the frontal area, and the downforce that are all important together, especially as you go faster with your RC speedrunning.
Thanks for watching. I hope that video gave you something to think about when it comes to your own RC speed cars. I mean, these are my untested theories, but they are based on science. I really like looking for any opportunity to bring some science into my hobbies and try and make things work a bit better with that background applied to it. I've already been testing these theories with my first speed car, the Cone that I mentioned earlier, up on the wall there. So far that got up to a top speed of 129 miles an hour. And it's, as we saw, it's really at the upper end of the speeds, 200 mile an hour plus, that these theories, you know, and whether they work or not, will really become clear. So let's see how things go with the Beast car as time goes on and I get to test it. In my next video, I'm going to get back on track and we're going to go into the Beast car body design, including the CFD analysis, and then follow that up with a build series. So keep an eye out for those ones. So please like, subscribe and share the video if you found it useful. So thanks for watching. Bye.